Today, I would like to prove one of my favorite theorems, the Heine-Borel Theorem. This theorem is one of the most fundamental and useful results of real analysis. The Heine-Borel Theorem also has one of the most visual and intuitive proofs that I have ever seen. And to understand the proof, you're going to need some real analysis basics, including the understanding of open and closed sets, sequences, limits of sequences, and the Bolzano-Weierstrass theorem. It is also useful to have some basic understanding of metric spaces, because you should know that everything in today's lecture is going to rely on the assumption that we're working in the standard Euclidean metric space. Otherwise, Heine-Borel theorem need not be true. One last thing before I begin. I want to give personal thanks to Siddhant Rastogi. To me, mathematics has always been the most beautiful form of art because the proofs, they are like magic. However, I wish mathematics was more accessible and that people enjoy the subject because it's a very lonely hobby. And to be honest, I stopped animation and mathematics for 3 years and been spending my income on partying and traveling. Now, on the animation side, making videos like these was a new idea, and new ideas always require refinement, and the backlash has been somewhat hurtful. And as for the mathematics may be beautiful, but studying it often feels like speaking to a void. Despite all of this, the message I got from Siddhant makes me feel very hopeful. Hopeful about the intelligence and ability of the next generation of mathematicians. So this animation is dedicated to him. The Heine-Borel theorem is a result about compact sets. And a compact set is a very interesting type of animal. Suppose you throw a bunch of open sets, typically infinitely many, on top of a set such that the entire set is covered. If this set is compact, then no matter what open sets were thrown on, you can always pick out finitely many of them so that our set is still covered by this finite collection. Let's make this into a formal definition. Definition. Let U be a collection of open sets. We say that U is an open cover of a set E if E is contained in union of this collection. A subcover S of U is a subcollection of U that is still an open cover for E. A set K is compact if every open cover of K has a finite subcover. And what the Heine-Borel theorem does is that it classifies all the compact sets of Rn. Namely, a set K is compact if and only if K is closed and bounded. Let's prove this in 2 parts. Beginning with the forward direction. Note that, in fact, the forward direction is true in any metric space. Heine-Borel theorem, forward direction. If K is compact, then K is closed and bounded. Proof. Let K be a compact set. The trick to prove the properties of closed and boundedness is just finding a slick choice of an open cover and then applying compactness of K. To prove K is bounded, we want to prove that K is contained in some bowl centered at the origin. So consider the collection of all possible bowls centered at the origin. U is equal to the set of all bowls centered at 0 with radius r, where r is greater than 0. U is an open cover of K, since its union is the entire space. So by compactness, K has a finite subcover S, which is just a finite set of bowls. S is equal to B subscript R I, centered at 0, where I is equal to 1, 2, all the way up to m for some natural number m. So K is contained in the largest of these bowls. Formally, K is a subset of B sub R0, where R is equal to the max of R1, R2, up to Rm. Now, to prove K is closed, it suffices to show that the complement of K is open. So consider an arbitrary point x in the complement of K. By definition of open, we want to find an open bowl Brx such that this bowl is contained in the complement of K. So consider all possible complements of closed bowls centered at x. U is equal to the set of Rn minus Brx closed, where r is greater than 0. Intuitively, you can think of the union of these sets as a closing circular hole that eventually covers everything except the center x. And because x is not in K by definition, U is an open cover of K. So by compactness, we have a finite subcover. S equals Rn minus Brix closed, where I is equal to 1, 2, all the way up to m, where m is some natural number. Define R to be the smallest radius, R equals min of R1, R2 up to Rm. Now I claim Brx is contained in the complement of K. This is pretty obvious from the schematic. But remember,
Math mantra. Pictures aren't proofs.
as a quick check, if Brx is not contained in the complement of K, then there exists a y in Brx such that y is in K. But that would mean that the complement of the closed bowl Brx does not contain y. Moreover, because the complement of the closed bowl Brx is contained every other set in S, the subcover S does not cover all of K, a contradiction. Therefore, Brx is contained in the complement of K, and so the complement of K is open. Now, to prove the converse of the Heine-Borel theorem, we are going to solve an easier problem. Instead of proving all closed and bounded sets are compact, it suffices to prove that closed boxes in Rn are compact. But to explain why this is true, we will need a basic property of compactness. Closed subsets of a compact set inherit the compactness of its parent. Lemma. Let E be a closed subset of a compact set K. Then E is also compact. Proof. Because the case when E is equal to the empty set, or E equals K, is trivial, let's consider the case where E is a proper subset of K. Let U be an open cover of E. We want to show that there's a finite subcover. And the trick to do so is to extend this cover to an open cover of the bigger set K. To do this, we just throw in the complement of E, which is an open set since E is closed. Define U prime equals to the union of U and the complement of E. Then by compactness of K, U prime has a subcover S prime. Now, we have two cases. Either S prime contains Rn minus E, or it does not. In the case of the former, S prime with this extra Rn minus E element removed must be a finite subcover of U. Otherwise, if S prime minus Rn minus E did not cover E, then S prime itself cannot cover K since it contains E. In the case of the latter, S prime is immediately a finite subcover of U. Therefore, E is also compact. Given a closed and bounded set E contained in Rn, we can surround this set by a box. To justify this formally, by boundedness, E is contained in BR0 for some R. But this bowl is contained in minus R comma R cross minus R comma R up to minus R comma R. So we can prove this outer box is compact, then by the preceding lemma, our closed subset E is also compact. but the proof that closed boxes are compact hinges on the classic result. Given a nested sequence of closed, bounded, and non-empty sets, their intersection is also closed, bounded, and non-empty. Because we know that closed sets are still closed under intersection, and subsets of bounded sets are still bounded, the only thing we really have to prove is that the intersection is non-empty. Weird. Lemma. Let C1, C2, C3, and so forth be a nested sequence of closed, bounded, and non-empty sets in Rn. Then the intersection is also closed, bounded, and non-empty. Proof summary. From our nested sequence of sets, construct a sequence of vectors by choosing one term at a time from each corresponding set. Apply Bolzano-Weierstrass theorem to get a subsequence that converges to X. For arbitrary I, all terms beyond the ith term of the subsequence is contained in Ci. Thus, X is in Ci. And since I was arbitrary, the intersections of all these Ci's must contain the point X. Proof. To reiterate, the fact that the intersection is closed and bounded is immediate. We only need to prove it's non-empty. And to prove that the intersection of our nested sequence of sets is non-empty, we need to find a point X with the property that X is in every set of the sequence. And to do so, we use a nice analysis trick. Suppose you're given a sequence of sets, and you want to find an X that satisfies some property. Form a sequence by taking a point from each set. As long as our sequence of points is bounded, we can apply Bolzano-Weierstrass, and then hopefully the limit will satisfy the property we need. First, construct a sequence by choosing a point in each set. Xk is in Ck for every natural number k. Since the sets are bounded, we automatically know that Xk is bounded. Applying Bolzano-Weierstrass theorem, there is a subsequence Xnj with limit X. Now consider any set Ci, and notice that I is less than or equal to Ni. Then, Xni, Xni plus 1, Xni plus 2, and so forth, is a subsequence in Ci, since Cni is contained in Ci, Cni plus 1 is contained in Ci, Cni plus 2 is contained in Ci, and so forth. But this sequence still converges to X, and since Ci is closed, X is in Ci. Since Ci was arbitrary, X is contained in the intersection of all these Ci's. Now that we've rewritten the problem and have the key tool to solve it, we can now begin our last proof. Theorem. Any closed box is compact. Proof summary. Suppose closed box B is not compact. Then for some cover U, B cannot be covered by finally many sets from U. Partition B into smaller boxes. Since B is not compact, at least one of these smaller boxes cannot be covered with finally many elements of U. By the same argument, we can construct a nested sequence of closed, bounded boxes that are not compact and cannot be covered with finally many elements of U. Apply the preceding lemma to find a point contained in every box. There is some ball centered at this point, such that it is contained in a single open set of U. Eventually, all boxes of our sequence will lie within this ball, contradicting that these boxes cannot be covered with finitely many elements of U. Proof. Let B equals A1B1 times A2B2 up to ANBN. Suppose B is not compact. Then for some open cover U, B cannot be covered by finally many sets from U. Partition B into 2 to the n smaller boxes by using the midpoints of AJ, BJ for each j equals to 1, 2, up to n. Obviously, at least one of these smaller boxes also fails to be covered by finally many elements of U. Otherwise, if they can each be covered by finally many elements of U, then so can their finite union B. This box in turn can be broken up into 2 to the n smaller boxes, where at least one of these boxes fail to be covered by finally many elements of U. Following this scheme, we can construct a nested sequence of closed bounded boxes, F1, F2, and so forth, such that each fail to be covered by finally many elements of U. Applying the preceding lemma, there exists an X in the intersection of all these Fi's. Moreover, since U is an open cover of B, X is an X for some open set X in our collection U. Hence, there is some R such that BRX is contained in X. But notice that our sequence of boxes are decreasing in size and eventually lie within BRX. Precisely, the diameter of F1 is delta equal to the square root of b1 minus a1 squared plus b2 minus a2 squared up to bn minus an squared. And so the diameter of Fi is delta divided by 2 to the 5. But for I chosen large enough such that delta divided by 2 to the 5 less than r, we have Fi is contained in the set Brx. But this means that Fi, and in fact all subsequent boxes of our sequence, can be covered by a single set of U, which is a contradiction. And as already discussed, the converse of Heine-Borel theorem is an immediate corollary. So we can conclude a set K is compact if and only if K is closed and bounded. Thanks again for your time. If there is any advanced, fundamental, or beautiful result you would like me to animate, please suggest it in the comments below. Thanks, and have a nice day.